My name is Marco Faella. I'm the author of Seriously Good Software. As you can see, that's the book webpage here from Manning Publications. I'm a professor of computer science at the University of Naples, and I've been teaching a advanced programming language class for about 15 years now. From this class, I got the idea for this book. The idea for the book is the following. From my teaching experience, I noticed that in a traditional computer science curriculum, you tend to have a lot of in-depth classes about different topics in computer science like algorithms and data structures and operating systems and so on and so forth. But I think what's lacking, at least I couldn't find a book that would present a global view over these topics and a way to compare and contrast these different topics. Particularly, I thought it would be helpful for junior developers or people studying programming to analyze all these different topics using the same example. So that's what I do in the book. I take a simple example, and in a minute I'm going to tell you all about this example. And I solve it many different times, again and again. And every time I try to optimize a different software quality. Now, what I mean by software quality is simply a property, a desirable property of software. Most of these qualities, as you can see from this slide, are commonly referred to as non-functional requirements. So you have efficiency that can be expressed in terms of time and space. And by space, I mean memory, of course. You have maintainability, usability, reusability, thread safety, robustness, correctness, and others. And these can all be seen as different forces that act on the programmer, pushing the programmer and the code in different directions. And of course, the poor working programmer also has to deal with deadlines. He has a limited amount of time, and usually this limited amount of time is a very strong force, and it's a force that goes against all of these qualities, because most of the time you're in a rush to deploy something, to show something to the client, and therefore you have little time to care about these properties or these non-functional requirements. And in the book, I also deal with a special property, which is succinctness, basically writing the shortest possible program for a given task. And that's rarely desirable, of course. It's just a fun exercise that I think it would be fun to add, a fun addition to the book. This here is the summary of the book itself. And tonight we're going to have a quick look at these chapters highlighted in bold. So chapters 1, 2, 3, and 8. But as you can see, there's much more material in the book. Tonight I won't be talking about space efficiency, reliability, and so on. Let's start with the example that's going to be developed in the book and in this presentation over and over again in different times to optimize different software qualities. This example is based on the idea of a system of water containers. So the basic object is a water container. It can contain a varying amount of water. And you have three methods interacting with these containers. You can measure the amount of water in a container with the getAmount method. You can add water to a specific container. And you can connect two containers with an imaginary pipe. And these connections are permanent. There's no way to remove a connection. This simplifies the implementation a bit, of course. And what's really important, is that whenever you add water to a container that's connected to other containers, that water that you're adding is going to be evenly distributed among all containers that are connected directly or indirectly to the one you're adding water to. In Java, that's the main language the book refers to. In the book, you also find C# references. So it's mainly a Java book, but there's little notes about C# here and there to connect what I'm saying to C#, to the equivalent C#. And also most of the content, most of the techniques I'm discussing are actually applicable to any object-oriented language. Anyway, back to our example. The API that I have in mind for my water containers is the following. getAmount returns the amount of water in this container as a double value. Add water, you pass it an amount of water, and you're pouring this water into this container, but remember that this water is supposed to spread over all containers that are connected to this one. And then you can connect this container with another. That's it. That's a simple use case. So I can build 4 new empty containers, A, B, C, and D. I add 12 liters or gallons, whatever you prefer, of water to the first container A. Then I add 8 units of water to container D. Then I connect the first 2 containers, and then I print the amount of water into the first container. The situation right now is depicted here on the right-hand side. We have 6 in A, 6 in B, because I poured into A, but then I connected, and the simple action of connecting them automatically distributes this water among A and B. C is still empty, and D contains 8 units. So far, so good. Let's connect B to C. Now, the 12 units that were distributed among A and B become distributed among A, B, and C, 4 each. And D is unaffected. So if I print the amount of water currently in A, I get a 4. And finally, let's connect B to D. In this way, all 4 containers in one way or another are connected. Directly or indirectly, it doesn't matter. The water will still distribute equally among all of them. And so we get 5 each, because the total amount of water that I initially put into them is 20. Now, in this example, I first added the water and then I connected the containers. But in general, I have to support any interleaving of these 2 operations. And I can add here, then connect there, then add somewhere else, and everything should work all the same. Now, I would like you to imagine your implementation of water containers, but your implementation should comply exactly with this API. Those are the rules of the game. So let's compare what you came up with my first implementation. I call it a reference implementation. So it's kind of a baseline that's a compromise between different software qualities or different requirements. And later in the presentation, we'll see how it compares with more specialized implementations. So my baseline implementation goes as follows. In each container, I have 2 fields. The amount of water in this container and the group of this container, meaning the set of containers that are connected directly or indirectly to this one, including this one, because it's easier if it's uniform, if I don't have to treat this container specially. Let's have a quick look at the constructor, for example. I will just instantiate, whenever I build a new empty container, I will equip it with an empty set of containers as its group, and then I will add this container to its group. So this set of containers start with a single element inside, which is the container itself. Sorry, this is going to be probably the most boring slide in the presentation, so bear with me for 30 seconds and I'll try not to show any long block of code anymore after this one. So this is a simple implementation of connect to. What do I do when I need to connect this container with another container? Well, first, I check whether they are already connected. This is important. Take a look here. To see if they're already connected, I simply check whether they point to the same group. So this check here is interesting. It's telling you that I intend to share these sets among all containers that belong to the same group. They're going to have the same set. They're not going to have different sets containing the same elements. They're going to link to the same hash set. So in this way, it's very easy to check whether two containers are already connected. They're connected if their sets, these group references here, are exactly the same. So if they're already connected, do nothing. There's nothing to do. The next 5 lines compute the new amount of water that should be in this container after the new connection. It's pretty simple. So I measure the size of the two groups that I'm merging. Then I compute the total amount of water that's currently sitting in those two groups of containers. So I'm connecting two containers, but in fact, by connecting two containers, I'm actually merging two groups. So in tot 1 and tot 2, I have the total amount of water in the first group before the merge, and the total amount of water in the second group before the merge. Therefore, the total amount of water in each container after the merge is going to be the sum of the two old totals divided by the new size of the group. So by the size of the merged group. And finally, with these 5 lines, I update all that needs to be updated. So I take this group and I merge it with the other group. Then I update the group pointer of all containers in the second group. I let them point to the new group, which is this dot group. And finally, I iterate over the new group and I update the amount of every container in the new group. The new group is obtained as the merge, the union of the two old groups. Not very interesting, just quite straightforward once we agree on these two fields, right? It's just a consequence of having chosen these two fields. In a second, we're going to discuss whether this is a good choice of fields or not, depending on our objective, depending on our goal, depending on the software quality we are aiming at. But for the moment, I hope it looks like a reasonable choice. And I hope this looks like a reasonable implementation for the connection method. Let's focus on time efficiency and see whether we can improve on our baseline implementation. So a little introduction first. How do we deal with time efficiency? So step 0, first of all, we try not to deal with it. So first question you should ask yourself is, do you really need more speed? You've probably heard the famous motto, premature optimization is the root of all evil, which means that programmers tend to optimize code too early or too much, even if it's not really needed. And optimizing for speed is not a neutral operation. So you're gaining speed, but you're probably losing on some other dimension, on some other quality. For example, you may lose readability. Your code may become harder to understand. So you should first ask yourself if you really need more speed. Then you probably should check the asymptotic complexity of your implementation. I hope you've heard of this. It's a fancy mathematical way of talking and measuring the trend for increasing size of the inputs. So if you manage to improve your asymptotic complexity, your theoretical asymptotic complexity of the algorithm you're using, it's very likely that you'll get a practical advantage, a practical improvement as well. After you have somehow achieved a good or optimal, hopefully, asymptotic complexity, you should switch to step 2, or you may switch to step 2, which consists of profiling and optimizing. By profiling, I mean you should guess, estimate, or measure 2 things. Usage profile. So how are your users interacting with your code, with your class, with your system? For example, in the case of a small class like our water containers, the usage profile boils down to how often do the clients call each method. We have 3 methods. They may be equally important or not, depending on the usage profile. And runtime profile, so measuring or estimating which methods actually take more time. Now, most people, when talking about profiling, they focus on runtime profiling. But as I'm going to show you in a second, in many cases, usage profile is also very important before you can optimize in the right way, optimize the right thing. When you do have this data, so when you do have an estimate of usage profile and runtime profile, then, only then, you should optimize. So you should refactor the most common or the most expensive method to gain the maximum speed. So you should focus your effort, your optimizing effort, on the method or the module of your system that's used more often according to the usage profile, and to the method or module that takes more time in practice according to the runtime profile. Back to our example. So let's start with the asymptotic complexity, and let's check the asymptotic complexity of the reference implementation. As you recall, we have a field holding the water amount in this container. Therefore, the getAmount method, which we haven't seen the code for, but it's trivial, just returns the amount that's written in that field. Therefore, the getAmount method is constant time, which in the big O notation is written as O of 1, which means its runtime is independent of the number of containers around, it's independent of the number of containers that are connected to this one, and so on. It's always the same, it's constant. On the other hand, connect to, which we've seen the code of, it contains all those loops, a couple of loops over all containers in the first group, in the second group, in the merged group. Therefore, its time complexity is linear. So it's proportional to the number of containers that are connected to this one, or more precisely to the number of containers that belong to the two groups that I'm connecting. And this we can write briefly as O of n, as linear. And finally, add water. When you add water, you also have to distribute it among all containers. So the add water method will also contain a loop over all containers that are connected to this one. So it's also linear. Question is, can we do better? And even before that, another question we should solve is, what does better mean? I think it's not obvious what better means, because we have three different methods here with three different complexities. So of course, if I can improve all of them at the same time, then it's better. But what if I can improve one while worsening another one, while increasing the complexity of another method? Is that better or not? So let's see in practice what I mean by this. So this is our reference implementation with its complexity. Now imagine we have an alternative one, another implementation where complexities are like this. So is this alternative better than the reference? Well, it clearly is, because I'm improving add water and I'm keeping the other two complexities the same. So this is better, and technically we can call it a dominating implementation. So this one, at least this time complexity table dominates this one, because on every row, this table is better than the old table. So let's say that alternative 1 dominates reference. Now imagine we have alternative 2, where the getAmount method goes from constant to linear, and the other two methods go from linear to constant. None of these dominates the other, because each alternative between these two improves on some method and worsens the situation on some other method, so they're incomparable. Which means that dominance is a partial order, and we can ask ourselves, what would be an ideal table? What would be an ideal implementation? Given that dominance is a partial order, we should be content, it's enough to have something that is not dominated by anything else, to have a table of complexities that is not dominated by any other implementation. This is what mathematicians call a Pareto optimal element, Pareto optimal time complexity in this case. Now, in our specific example, let's search for a Pareto optimal implementation by taking little steps. So first of all, we start from reference. can we just improve add water to constant time? By changing the class, of course. You cannot just change the implementation of add water. You have to make a pretty substantial change to the class. And the answer is yes, we can do that by having a separate group object. Instead of just a hash set, we add a nested class called group, and each container will have a single field which is a pointer to a group object. And what does the group contain? The group object contains the amount of water per container and the set of its members. So basically we are moving the amount variable from the single containers to this other object, which is called a group. And then all containers that share the same group, so all containers that are connected, will point to the same group object. And this will make add water much faster because it won't need to iterate over a number of containers. It will just need to update the group object. I think this picture will help you get a mental model of what's going on. So in reference, you have in each container, this is the situation in the use case I showed earlier. So when you have 4 containers and the first 3 are connected, in the reference implementation, the first 3 containers point to the same hash set. And the hash set, in turn, points back to these objects. But the amounts, the water amounts, are located within each container. On the other hand, in this new implementation, which I'm nicknaming Speed 1, so it's the first speed optimized implementation, the water amount is sitting in the group object. And now the containers themselves, they only have a link to a group object. And then the group object contains a water amount, which is to be intended as the water in each of these containers, and a pointer to the hash set. And I'm sure you can see how with this architecture here, we get those time complexities. So add water is fast, is constant time, because it just operates here. Get amount is still fast, because it only needs to access this group object. And connect to is still linear, because you still need to merge these sets and then updates these amounts into a single group object. Let's move on. Can we get this table of complexities? Remember that reference is like this, and this is what I previously called alternative 2. So can we add water and connect containers in constant time? This is the tricky part. I want connect to be constant. But I'm okay with raising the complexity of get amount to linear. How we can do this? We can do this with 2 tricks: circular lists and laziness. What I mean is the following. So first, notice that 2 circular lists can be merged in constant time. So suppose that A, B, and C are connected, and I represent this by linking these containers in a circular fashion. A points to B, B points to C, and C points back to A. It's a circular list with 3 nodes, and the nodes are the containers themselves. And D is isolated, and suppose that when a container is isolated, it has a next pointer which points to itself, as is commonly done with the circular lists. Now, if we simply swap the destinations of the red and blue pointers, we just swap these 2 pointers, we obtain a single list, circular list. So B was pointing to C and D was pointing to D. If I swap them, then B will point to D here, and D will point to C. So as you can see, it's a single list now. And that's the trick we're going to use to connect 2 groups in constant time. Now I still have to tell you how I'm also going to obtain constant time add water. And here the trick is laziness. So in other words, I'll implement these 3 methods as follows. Connect to, start from connect to. It will merge 2 circular lists, which is a very fast operation, and it does not touch the water amounts. It leaves them, it doesn't distribute water. Even add water does not touch water amounts except for the single container where I'm actually pouring water. So it will just add water locally. Okay, this is, for the moment, the water amounts are inconsistent. I'm adding water locally and I'm not distributing it yet. Whenever I call getAmount, I iterate over the group, I check the total amount of water, and I fix the amount of water in each container. So I'm distributing water as late as possible, only when the client actually needs the updated amount. This is a trick commonly called laziness. Okay, so before returning the amount, I distribute water. And this way I get this table. And this table is incomparable with the one for reference. Quick look at the implementation of this last version. So each container will have an amount field and a next pointer, and connect to, when I pass another container, simply swap their next pointers. Clearly, it would be great to do everything in constant time. I think you realize, if you think about it, since there is this non-local effects, so containers are connected with each other, there is some non-local action. So when I pour water and then I ask the amount of water, at some point the object needs to talk to other objects. So for this kind of reason, we cannot do everything in constant time, but we can get pretty close to it. We can get pretty close to constant time using a family of algorithms known as the union find trees, using these data structures. These are a classical data structure for maintaining disjoint sets. And in our case, the disjoint sets are the groups of connected containers. And the way they work, I will not go into the details, I'll just give a very high-level overview. But the general idea is that you have a set of elements, and in this case they are the containers. And initially each element is isolated. And you have two operations. Union operation, given two elements, merge their sets. And find operation, given an element, obtain the representative of its set. So in other words, when you use this data structure, you merge elements into groups. Each group has a representative, and then you can iteratively merge groups with other groups. And after the merge, they will have a new single representative. So for example, if you want to check if two elements are in the same set, you call the find operation twice. It will give you two representatives. And if their two representatives are the same, then those two elements belong to the same set. Without going into details, let's just say that the trick to have an efficient implementation is to represent each set with a parent pointer tree. So with a tree whose nodes point to the parent and not to the children. If you use this representation, then the union operation consists in merging two trees, and the find operation returns the root of the tree. So the root of the tree is going to be the representative for that set. Now, what's the complexity of these union find trees? It turns out that the worst case complexity is that using union find trees, we can implement our three methods in logarithmic time. If you compare it with the previous tables, this is another incomparable table. Some things are faster, but some things are slower than the previous implementations, because log n, a logarithm, is slower than constant, but faster than linear. It sits in between. However, this worst case complexity is not the best way to measure the complexity of union find trees. Let me remind you that there's three main ways of measuring the complexity of an algorithm or a data structure. There is the most common one is the worst case complexity. It's the complexity given the worst possible input or the worst possible use case. Then we have average case complexity, which is a probabilistic measure, is the average complexity over a given distribution of inputs. And then you have a third important way to measure complexity, which is called amortized complexity, which consists of an average complexity over a long sequence of operations. And you need to use amortized complexity. So in other words, that's the most appropriate way to measure complexity whenever you're dealing with algorithms or data structures that make investments, so that make some computational effort now to get some future benefit later. And that's exactly the case for union find trees. As a matter of fact, if you imagine so speed tree is the implementation based on union find trees. And if you measure the complexity of a sequence of M operations on N containers, so a long sequence of operations, you get an amortized time complexity, so an average complexity for the whole sequence of operations of M, which is the number of operations, times a special function called the inverse Ackermann function, denoted by alpha, of N, where N is the total number of containers. Now, the good thing about alpha is that alpha of N is at most 4 for all N up to 10 to the 80. So 1 followed by 80 zeros. So in other words, the inverse Ackermann function is essentially constant. It's not formally constant, but it's essentially constant. You can replace it with the number 4, which is a constant, up to humongous numbers of containers. Therefore, the practical complexity of this sequence of M operations is just O of M, is linear in M. But this is a sequence of M operations, so it means that the average cost of a single operation is essentially constant. So for all practical purposes, the real average complexity of an operation on speed tree, which is the implementation based on union find trees, is constant. If you're still not convinced by all this theoretical hand waving, in 2 minutes I'm going to show you the results of actually running, of performing a benchmark test of this implementation, and we'll see what happens. Before I run these tests, let me show you a picture taken from the book. So in this picture, I'm comparing a couple of implementations. Some of them we've seen it so far. They are reference, speed 1, speed 2, which is the one with circular lists, and speed 3, which is the one with union find trees. And then it also includes memory 1, memory 2, which are other implementations that you can find in the next chapter. We're not going to talk about them here. But you should know that these are the implementations that try to optimize the memory occupied by each container. And in this graph, you have space on the x-axis. And by space, I mean the average number of bytes per container in a standard scenario with the 1000 containers connected in 100 groups of 10. So a reference, for example, needs almost 60 bytes per container. It's very expensive memory-wise. And on the y-axis, I put the complexity of the slowest method of the 3 methods. So as you can see, reference sits here at 60 bytes per container, and the slowest, with the slowest method being linear. And speed 3 here, the one with trees, is a lot more space efficient, fewer than 30 bytes per container, and also the slowest method is essentially constant, because all 3 methods are essentially constant. And then you have different combinations. So for example, in a different chapter, we have a memory 3 and memory 4, which squeeze each container in fewer than 5 bytes. But on the other hand, they increase the complexity to linear here and even to quadratic here. You can find all the details in the book if you're curious. And finally, let's move to the final step in the time efficiency spectrum. Let's run some tests after all this theoretical analysis. For example, we could do these 2 experiments. First experiment, 20,000 new containers, so 20,000 invocations to the constructor, 40,000 calls to add water, 20,000 connect to, and so on. And this is the time in milliseconds. We have reference implementation takes 2 seconds to do all of this. Speed 1, 26 milliseconds, 500 milliseconds, and 6 milliseconds. This is what I get on my laptop. So as you can see, Speed 3 wins with a huge margin over the others, particularly over the first one. It may be interesting to do a slightly different experiment, well, a quite different experiment, where I only do one final call to get amount. And this is the best possible scenario for Speed 2. Speed 2 is the lazy implementation that delays all the operations, all the heavy operations, until you actually call get amount. And this laziness really pays out in this scenario here, because in this scenario, Speed 2 manages to be even a little bit faster than Speed 3. So this proves the usage profile, how your clients are going to use your class, can have quite a big impact on your numbers, on your practical performance. Summarizing, we're finished with time efficiency. First of all, before you dive into this deep and somehow complicated analysis, you should really ask yourself if you need more speed. Then you should have a look at asymptotic complexity of your algorithms, because those are going to have a big impact in general. And don't forget that there's various forms of asymptotic complexity, not just worst case, but also average case and amortized. And finally, after you are satisfied with your asymptotic complexity, you can move to your practical measuring and optimizing. Don't forget to pay attention to your usage profile, and don't forget that in some cases you can get an improvement by simply shifting the effort, the computational effort, from one part of your project to another project. So it doesn't just become faster. There's nothing becoming faster, but by just moving the heavy lifting to a different parts of your project, you can get a practical benefit depending on your usage profile.